Okay, so we now come to the second chapter uh, regarding the analog instruments. Okay, uh, so analog instrument is the uh, forefather of the electrical measurement device, uh, but the analog instrument is still relevant until today and can be widely seen or available or in the market. Okay. All these analog device, they originated from a device called the unsolvable meter movement. Okay, the unsolvable meter movement. Okay, so this the unsolvable meter movement can be basically modified or configured. Can be configured to be used as an ammeter, and can also be used as DC voltmeter, and also can be used as a ohm meter, okay, with a proper modification or arrangement. That basically what we're going to see in this lesson. Okay, and the ammeter, both ammeter and voltmeter can basically be used to measure DC or AC signals. Okay. As you can see, the proper method that is required, like for example, to how it can be used as a DC ammeter or there's a method called multiple range DC ammeter using Ayrton shunt. So we will look into that configuration in this lesson. And in this, there's a important concept what is called as insertion effect. So insertion effect is the uh, thing that you must consider before you design an emitter and before you use an emitter. Okay. It will uh, determine the accuracy in the performance of the emitter. Okay. Uh, like DC voltmeter, okay, can be used as a DC meter using air attention, but with a different configuration, okay, different configuration, and then there is a important concept called as loading effect, loading effect, which also involve uh, the uh, performance of the DC voltmeter. Okay, next we have AC for ammeter, which can be used by modification, okay, method called as full wave rectifier, and also DC voltmeter method called half wave rectifier. Okay, we will look into that. Okay, so what's the difference between analog and digital? Okay, for an analog device, the amount of deflection is analog, means that it continuously change over the time. Okay, uh, and then the value basically can be related to a linear deflection, linear deflection of a needle. Okay, this is an example. You see the picture, an uh, example of an ammeter. Okay, whereas on the face of the ammeter, okay, there are needle, a moving needle, and there are scale, okay, on the top. Okay, and the scale, so it is showing the value of the basically the deflection. and deflection of the needle. And the deflection is basically in relation with the amount of current. Okay, amount of current that inserted or flow through the analog emitter. Whereas for digital, it depends on it based on the discrete value. This discrete value, uh, discrete value, discrete value of current. Okay, and then the information is represented by discrete value of digits. Okay, and usually a digital meter will show you a discrete value, in the form of numbers on the LCD display. Okay, so it basically shows you a discrete value, and the discrete value is depend on the resolution of the digital meter. Okay, so in general for analog device, the action or the deflection it, depends on the deflecting torque produced by an electrical current. So it is important for you to call back your understanding about the concept of motor. The motor, so basically, how does a motor work? A motor, uh, you have a loop. A simple motor, you have a loop carrying current placed inside the permanent magnet field, and then the current that flow through the loop or the conductor will generate its own magnetic field, interact with the permanent magnet, and then there will be interaction, and then uh, just convert the electrical energy into mechanical movement. So then you have a rotation. So, so it's good for you to recall back your understanding about motor. So analog device, measurement device, numerical measurement device, they share the same concept of a simple motor, electrical motor, but with some modification that we will look into later. Okay. Uh, so even a current or ammeter or voltmeter, okay, the deflection is due to the current that flow through the device. Okay, but in ammeter, the deflection is proportional or in relationship with the current, whereas for a voltmeter, the the deflection is in relationship with the voltage value. So later also we will look into how it can be related. Okay. In essentially either voltmeter, ammeter, or even ohm meter, they are current measuring devices. Okay. Fundamentally, they are current measuring devices. So it all depends on the configuration, how we configure, and then how we interpret the output or the outcome. Okay, we just give some credit to the people who founded the concept. Okay, the term, the galvanometer or permanent magnet moving coil or the unsolvable device, so they are referring to the same concept or same device. Okay, so galvanometer derived from the name of the person who, who found it, the surname, okay, Luigi Galvani. Uh, and many applications measuring for the accelerated with William Thomson or Lord Kelvin. And the earliest governor was voted by the person called as Johann Schlegel and Nuremberg at the University of Halle. back in the 19th century. Okay. Uh, so Andre Mary MP also contribute to the development of galvanometer. So here the person who the person who the name who coined as a unit of current, okay, electric current. And of course, these physicists use the device developed by the previous people, called as a galvanometer, to prove the concept of current flow in a circuit. So this is the history. Don't want to go that. The the look, the general look of the galvanometer of PMMC or the ensemble devices remain the same. Okay, they have needle, so they have the window, okay, where you can see the needle and also the scale. Okay, and then also they have the terminal. The terminal basically terminal where you insert the input and the positive and negative uh, wires. Okay, so these are the types of analog meters. Okay, the analog meter, the first one is the called as permanent magnet moving coil or PMMC. This is uh, the general or the fundamental type, the PMMC. Okay? PMMC, and then basically it is used to measure direct or alternating current and voltage. Okay. Then they have the moving iron meter, DC and AC. We have the dynamo, electrostatic, and induction type. So they are the others are basically derivatives of the analog meter, okay, which basically the principle, okay, a bit quite different, and then group into a different type of analog meters. And then maybe we will look into the later, or maybe we will look into the principle one by one, and also the usage of the analog meters. Okay, now we have come to the unsolvable galvanometer. Okay, so this is basic based on the principle of moving electromagnetic coil. Okay, and you imagine okay, as you can see from the picture, okay, there is a electromagnetic coil, okay, in the middle. It's basically winding of wires. Okay, it's basically a piece of conductor. Okay, a long conductor, but wound into a on a cast or on a shape. Okay, okay, as you can see in the green color, so it's like a core. Is and then the pink color in the middle is basically the wire is wound, okay, wound, okay, on the core is basically that's in a core. It's like a case, a casing. Okay, and this casing is basically suspended, okay, on the support. Okay, you can see the blue support. Okay, the blue support. So it is suspended on the there's a tip, okay, on both ends of the green, okay, green part there. Green part, there's a case, the green part. Okay, there's like a needle. Okay, the needle. Okay, so it ensure that coil, okay, the coil can rotate freely. Okay, can rotate freely, okay, and basically there's a set of a spring attached to the core. Okay, okay, there's a core, iron core, and then the case. So basically, the iron core and the case they are attached together. They are rotating, and there's a spring. This spring basically attach, okay, to the moving part with the support, okay, on the front and also at the back. So the purpose of the spring is to limit the rotation. So if you recall the concept of electrical motor, so electrical motor basically they are rotating freely. Okay, they are rotating freely. Okay, rotating freely, and then when you increase the current, they will rotate faster. They rotate faster. But in this case, okay, in this case, uh, we limit the rotation. Okay, it will only rotate, for example, from 0 to 100 degree on a 0 to 100 degree angle. So we limit. And also the purpose of the spring is to limit, uh, to oppose the force that producing the torque, so that we can read, or we can know the amount of force that produce the deflection or the rotation. Okay, and that amount of force is proportional to the current that flow into the conductor. Okay, so we will look into that in detail later. Okay, uh, so the thing is that, uh, the interaction between the fixed permanent magnet with the coil, with a coil of wire, we make it to turn. Okay, we will look into that in details. Okay, this is what I explained about the case of the conductor. Okay, okay, on the side, okay, the outer side of the case, specifically the piece of conductor, okay, piece of conductor wound on the outer side of the case. Right? Okay, on top of the case and the bottom of the case, there are a needle of pointy support. Okay, this is a pointy support. Okay, they are basically will, okay, place on the support, and then you will make sure that the, okay, basically this is the conductor, okay, will rotate. Okay, and then the hairspring is placed on the one end, is placed this end of the needle, okay, attached to the needle support. This is not needle, the pointy support. Okay, and the other end is mounted or attached to the support. Okay, the support like this one is the blue support here. Okay, in the picture. Okay. So the thing is that, uh, when when there is no current flowing through the conductor, means that there is no deflection torque. There is no interaction between the magnetic field, the generated magnetic field by the conductor with the permanent magnetic field. So there is no rotation. So when there is no rotation, the hairspring, he will, he make sure that the conduct, so basically make sure that the spring will make sure the case, the rotating part return to its original position. Okay, okay, you can see from the analog meter, okay, when there is no current, the needle will always start on the left, on the left. Okay, when you give current, it will deflect depending on the amount of current. It will deflect, and then it will stay at the position. When it stay on the position or remain uh, uh, when the needle is deflect and then stay at the position, it means that it has reached an equilibrium where the amount of force producing or deflection force equivalent to the force, okay, the opposing force produced by the hairs or the spring, the hair spring. Okay, okay. So the purpose of the hairspring is to oppose, okay, the amount of force produced by the deflecting torque. Okay, the deflecting torque. So like I explained, the interaction between the magnetic field from the magnetic field and the coil is equal to the force of hairspring. Okay, means that when when current, okay, is insert into the, okay, into the conductor, okay, so when current flow into the conductor, as you can see from the figure on the bottom, if the current, okay, this is current, the I inserted, okay, to the conductor, okay, then the magnetic field produced on the conductor, on the sides of the conductor, will interact with the permanent magnetic field. Okay, permanent magnetic field. Okay. So basically, that is what it's called as the uh, torque, the deflection torque. Okay, so the deflection torque, okay, basically will be proportional with the current FD, deflection torque. Okay, deflection torque. So the current, okay, that flow will be proportional to the the deflection torque. Okay, FD, deflection torque. Okay, so and then is it will be equivalent to the angle, okay, of deflection. Let's say this is, okay, uh, 0 to degree. But how do we get that deflection, or how do we get, so how we make the conductor here, or the rotation limit to a point? Okay, how do we get? It depends on, okay, the amount of deflection torque and also the amount of the opposing spring. Okay, of course, when spring is compressed, okay, as when it compress, it will create an opposing force. Okay, if it is compressed further, the amount of opposing force will be greater. Okay, will be more greater. So when, okay, basically the deflection torque, okay, is equivalent to the opposing torque by the spring F in negative spring. Okay, so that is when, okay, that is when the deflection or the pointer stay at a position, stay at the position. So at this point, we say that the deflection torque, F deflection torque, okay, minus F spring will be equivalent to zero. Okay? So it's like in physics. Okay, if you have force in one direction, and then there's another equivalent force at another direction, the object will remain idle or remain at that position. We will not move further or move backward. Okay, it will remain uh, at the one position. Okay, so the PMMC working principle here. The electromagnetic torque is counterbalanced by the mechanical torque produced by the spring. Okay, the spring. Okay, and like I explained, the balance of the torque and therefore the angular position is indicated by the pointer against the fixed reference called a scale. So we have a scale. So here our scale is pre-calibrated. So we pre-calibrated the value, okay, depending on the scale that we want to, okay, for it to show. Like for example, we have calibrated it measure from 0 to um, 10 ampere, for example, 10 ampere. So we know that the rest is just 1, 2, 3, 4, 5 is just the uh, the division of the maximum. Okay, for example, so here 5 we have like what, 2.5, 2.5 is 5, is it? Or I'm not mistaken. So the 1, 2, 3, 4, 5, 6. Oh, sorry, 6. So there's a bit odd number, but anyway, then we know that the second scale here they should show 10 divided by 6, is it? And so on. Okay, 1 multiply with 10 over 6, and this is 2 multiply 10 over 6. I can figure out this the scale that I made up. Okay, so the scale the scale value we calibrated when we will of course see how it is done later in the for the lesson. Okay, okay, so the torque or the developed torque, okay, given by this formula, okay, torque, where the torque is proportional to the flux density. Flux density of the permanent magnet. Ini permanent magnet. Okay, we have a permanent magnet. We have the magnetic field. So the is proportional to the permanent magnet, and also proportional. The torque is also proportional to the effective coil area. Okay, the coil area. Usually the coil area. Okay, in coil, so the coil area basically like like a rectangle. Okay, you can find the effective area by finding the length and width. Okay, and also it is proportional to number of turns. Okay, and number of turns, and also proportional to the current value, current that flow into the coil of the movable coil. Okay. So and so this is the equation of the torque. Okay. This is a further explanation of how it works. Okay. So you can recall back the concept of simple motor. Okay, you have a conductor, okay, a piece of conductor, but in our case here, our conductor have multiple loop, multiple winding. Okay. So, but basically, it is a piece of conductor, just a piece of conductor. a wire. Okay? And then when current flow, okay, wire flow to the conductor, it will generate its own magnetic field depending on the direction of the current. Okay, if okay, and on this side, the current is going. Okay, okay, if we look, it's going out, and this direction is going in. Okay. So those are the direction of the magnetic field interact with the permanent magnetic field. Then the for each side, okay, the force produced on each side is complementary of each other. They are not opposing. They are complementary each other, meaning that the amount of force producing on each side make it turn at the certain direction or certain okay, in this case it turning clockwise. Okay, it turning clockwise. Okay, but again, in our application we have a spring, okay, that limit the rotation. So the torque that producing, okay, the current, okay, will be opposed by the counter torque produced by the spring. Okay, counter torque by the spring. So when the deflection torque equivalent to the counter torque by the spring, the needle will, okay, which obviously attach, okay, for example it attach, it's somewhere here attach. Okay, wait, what? So the needle, the indicator, okay, the needle that indicate the rotation on the scale, it will also deflect, okay, and then show us the value. Okay, basically it show us here what is this value. Okay, okay, the value of current. Okay, okay, so that is the fundamental how, okay, we can relate, okay, the current value with the deflection torque. Okay. Okay, so these are the assembly, the practical assembly of the PMMC or permanent magnet moving coil, or PMMC, permanent magnet moving coil. So this is the practical, okay, the practical uh, arrangement of the PMMC. Okay, the iron core is placed inside the core. Okay, this is the iron core. Look like a cylinder. Okay, the purpose is to concentrate the the magnetic field. Okay, both in this case to concentrate the generated magnetic field, to concentrate, and then they have a curved pole attached to the magnet to ensure the turning force on the coil increase set steadily as the current increases. So to make sure the current is proportional to the deflection, or to the deflection top in the in, so to make sure it is linear. So these are the advantages of PMMC. They can be modified. PMMC can be modified with the help of shunt resistor. Okay, modified into current or voltage device. Okay, device. They display no hysteresis. Hysteresis, uh, as mentioned in the terminology, hysteresis is the deviation of the uh, exact output with the expected output. So basically, they in ideal condition, they don't exhibit that characteristic. They also does not affected by uh, the magnetic field produced from other devices. Okay, so they can not they can remain functioning or properly functioning when there are, or even though there are other magnetic field uh, comes near to the device. Okay, and these are the disadvantages due to wear and tear. Okay, so if you know, because it depends on mechanical movement, so at some point it will lose its accuracy. Okay, uh, especially the friction on the support, on the pointy support. Okay, the pointy support where it is attached, the moving coil attached to the support, the main support. Okay, so that is basically a bit sharp, and then it can cause friction. But at some point, if you use it properly, basically if you use it properly, store it properly, don't uh, uh, expose it to unnecessary vibration or external, like for example you just do not handle it properly, you throw it when you want to store or want to put it away, you just throw it away, so it will easily damage. Okay, because in general the parts are fragile, so you must, especially when you want to use it or you want to transport, you want to moving it somewhere else, you have to properly handle it. Okay, these are the other types. Okay, the other type, but I think we'll stop here. Yeah, thank you. If you have any question, okay, you can always drop the question on the class, on the WhatsApp group. Okay, I conclude my lesson for today. So thank you very much.